Hello. So now we are in a position to understand Carnot engine. Carnot engine is an ideal heat engine. It comprises of reversible processes which are not real processes. So Carnot engine cannot be actually constructed. It cannot be realized actually, right? It cannot be realized. Okay. So, there are four processes which I told you, that heat addition, one can say expansion where you get work, heat rejection and work input, right? These are the four processes. And Carnot said that all these processes should be reversible if you want to construct an ideal engine. So all these processes are reversible. Now first let's say heat addition. Okay. By the way, here I have drawn a engine schematically, and this is TH is the temperature of the source, PL is the temperature of the sink, H for high temperature body, L for low temperature body, and QH is the heat received by the engine from the source, W net is the net work the engine gives out, and QL is the heat rejection to the sink. Okay. You might note here this E, right? E is for engine, but it's kind of reversed or inverted. I mean, it's reversed, right? It's a mirror image, one can say. So why this? I'll come to that later. Okay. So first process is heat addition, and Carnot said that this process has to be reversible. And you know that reversible heat addition is a heat transfer. Reversible heat transfer can happen only when the temperature difference between the two bodies between which the heat transfer is taking place, the temperature difference is infinitesimally small, right? So this is how the source temperature, if it is TH, then the engine must be receiving the heat while itself being at a temperature of source. So the temperature difference between them should be infinitesimally small, right? So imagine this a piston cylinder arrangement. There is some gas, some fluid. Carnot doesn't talk about any fluids, but we will say there is some fluid. Okay. Then we are saying that I've shown the body TH, that is reservoir, that is source, from which heat is given to this fluid. But remember that this is insulation, right? So the piston, the cylinder is insulated. Okay. It's insulated even from here. There is no scope for heat transfer. Heat transfer would take place only when there is heat addition and heat rejection. Otherwise, there is no heat transfer from the fluid to the surrounding or from the surrounding to the fluid. So the first process is heat addition, which has to be reversible heat addition. So we imagine that from the top side, heat is transferred, let's say, and this is TH body, source body, that is brought in contact with the fluid inside. And obviously it's a reversible heat transfer. The temperature of the fluid inside would be close to TH. So it's infinitesimal temperature difference, and amount of heat transferred given is QH. Okay, fine. When this is done, when heat addition takes place, obviously the temperature of the fluid, you can say that it will be temperature TH, because heat is transferred reversibly. It's going to receive the heat, while it itself is at the temperature TH, and then the heat transfer takes place. So it is a reversible heat transfer. So if I want to show this on a PV plane, let's say the fluid is at point 1. This is our point state. State of the system is, our system is this fluid inside, right? So I am showing the dotted line, if at all, and heat is received by it while it itself remains at temperature TH, that is the temperature of the source. And so it's an isothermal process. There is a reversible heat addition and it is also isothermal. I need you to be very carefully paying attention. Why it is isothermal? Because this temperature is constant, so obviously the temperature of the gas has to be constant, because you want reversible heat transfer, right? So since your need is to have reversible heat transfer, this temperature and this temperature should be same, that because this is constant, this also has to be constant. So heat transfer is, heat addition is reversible and isothermal. So isothermal process here is shown like this, right? So this is, I can say 1 to 2 is a isothermal process, and it is also reversible. So it's a reversible isothermal process during which QH amount of heat is given to the engine. Fine. Then what happens? Then this insulation is brought over here, so the entire thing is completely insulated. There is no heat transfer, and let's say the gas or the fluid here expands, right? So remember this, expansion is taking place when there is no heat transfer allowed, because this is insulated now. So it is adiabatic, right? It is adiabatic heat transfer, adiabatic expansion. There is no heat added or no heat leaving from the fluid, and this expansion has to be reversible because all the processes have to be reversible. So it is a reversible adiabatic process. Reversible process which you would imagine to be taking place very, very slowly, right? Every time the system would pass through infinite equilibrium states, right? Quasi-static process, you can recollect that. And so it's a reversible and adiabatic expansion. So you can say, let me complete this. So this is point 3. So 1 to 2 is heat addition, 2 to 3 is expansion, which is reversible and adiabatic, during which you will get some work. Okay. Then when the piston is expanded to point 3, volume has increased, then what happens? Let me stretch this line. Then the piston starts moving towards left. So there has to be, when it is expanded, now the piston will start moving towards left, but now the heat has to be rejected because all the heat cannot be converted into work. So now this body, the insulation is removed, this body is brought in contact with the fluid, and again there is heat transfer. This heat transfer is again, remember this, it is reversible heat transfer. Meaning what? Now the body which is brought in contact is, that is sink, the temperature of the sink is TL, low temperature. The fluid should also have the same temperature as this, because only then the heat transfer would be reversible. Okay, only then heat transfer will be reversible. So this body is brought here, heat is rejected, and so it's a reversible heat transfer, and also it is isothermal. Why? Because this temperature is constant. If this temperature is constant, the temperature of the fluid which is giving the heat, that temperature also has to be constant, because the process has to be reversible. So it's again a isothermal process. Okay, and during which there is compression taking place, but it's isothermal, right? So during which heat rejected is QL. So let's say this is point 4. 3 to 4 is heat rejection, isothermal and reversible heat rejection. And after that, right? So after that, when the heat is rejected, QL amount of heat is rejected, again this body is removed and insulator is placed, right? And again this further compression, now the system has to be going back to state 1. So this is going to be a compression, but this is going, so that means there will be some work done on the gas because the piston is moving, and that process remember is again reversible, right? And it is adiabatic because it's completely insulated. So again a reversible adiabatic, one can say, compression. So it's a reversible . So this is, let's say this is point 1. So reversible adiabatic compression. So again the system has come back to initial state. So please note, this is from 1 to 2 the temperature of the gas is TH. From 3 to 4 temperature of the gas is TL, right? 1 to 2 is reversible and isothermal heat addition. 2 to 3 is expansion. What kind of expansion? Reversible and adiabatic, during which you can get some work. Okay. Then 3 to 4 is heat rejection. Again it is reversible and isothermal heat rejection. Okay, and it is heat rejected at TL. TL is the sink temperature. And 4 to 1 it is reversible and adiabatic compression. Okay. Now here please note, 4 to 1 there some work is done on the system, right? And that will be work input, which I can show like this. But that work, if you subtract, and I can write here is W net, right? So or we can say it is W and this is some pump work, some compression, right? So that is WP, and this W minus WP, I can remove this and say W net. Okay, so this is on a PV plane. I'm sorry, I forgot to mention this. This is PV plane, and now here look at this. This is your schematic diagram where of a heat engine. I have written this E like this. Instead of writing E like this, I have written this kind of reverse, inverted, whatever. Why? Just to signify that now this engine is reversible. That means it can be reversed. What do you mean by that? Reversible means see this is W net, that is the work output. Just now, now in this engine, QH is supplied reversibly, isothermally. W net is the work output, and heat rejected reversible and isothermally is QL. Fine. Now suppose you reverse this work, you give exactly same amount of work W net, then this engine can pick up QL. This arrow also gets reversed. It is picking up heat QL from the sink, again reversibly and isothermally, etc. And QH will be delivered, right? QH will be delivered. So all the processes can be reversed, and there will be no change in the surrounding. You are taking exactly, if this engine is part of system and W net is the work done on the surrounding, then take exactly W net from the surrounding and all the operations will be reversed. So this becomes a reversible engine. So Carnot engine is a reversible engine. Someone can say reversible engine or Carnot engine. It's the same when we are talking here. So it's a reversible engine, it's a Carnot engine. And now in this, when you say Carnot engine, how do we see efficiency? Let's talk about efficiency, and that's the last point. See, efficiency of any engine is net work W net upon heat supplied, right? W net upon heat supplied. Now what is W net? It is QH minus QL, right? QH minus QL. So we can, this is heat supplied is QH, right? W net is QH minus QL upon QH, right? Now this is the efficiency of any engine, okay? Any engine. If this engine is reversible, that means if it is a Carnot engine, then this efficiency is also equal to TH minus TL upon TH. So efficiency of Carnot engine is function of source and sink temperature. Function of source and sink temperature. So if it's any engine, right? Any engine which is not may not be reversible, may not be Carnot engine, but which is operating between the same temperature limits TH and TL, then you can find out efficiency with this QH minus QL upon heat supplied. I'm sorry, heat supplied. QH minus QL upon QH heat supply. But if it is a Carnot engine, this is also equal to TH minus TL upon TH. Remember, this is also equal to TH minus TL upon TH. So Carnot engine, efficiency of Carnot engine depends only on the temperatures of source and sink. Okay, source and sink. So I don't have to repeat, but remember, efficiency of, because this is a mistake which students always do. A Carnot engine is the best possible engine that can be imagined. Its efficiency is never 100% because it is also bound, or it stays in the limit of second law. So efficiency of Carnot engine is never 100%, but it is maximum for a, and we will prove that, that's known as Carnot theorem, which will be next video. But it's never 100%, but for a given temperature range of TH and TL, efficiency of Carnot engine will be maximum. Carnot engine also has to reject the heat, so it cannot have 100% efficiency. Thank you.